and we're going to be talking about exponentials today. So let's go ahead and let's share that with my PowerPoint, which is right here. And let's go ahead and take this from the beginning, see if that'll work. Hopefully this is going to look okay to you guys. So we're going to be talking about exponential functions and a little bit about how you graph them. So here's the first slide that we have, this is what an exponential function looks like. And I want you to notice that A is considered to be a constant. I know when you look at A, you don't see a constant, you see a variable. But consider A to be a constant. And it says A is some number above 0, but it cannot be the number 1. So what could A be? Some number above 0, but not specifically 1. A could be 2. What else could it be? 1/2, absolutely. Could it be 1.3? Now, why would it not be the number 1? What happens if you take 1 and raise it to the x power? It would just be 1 no matter what x is. It's a horizontal line. That's not what we think of when we think of exponentials. Now, have you guys heard of the idea of exponential growth? I hope you have heard about it. That's the scary part of pandemics, because what happens when one person gets it? They spread it to a few more. What happens when a few more get it? They spread it to a lot more, and then those people spread it to a lot more. That's kind of how just viruses spread or any kind of infection. We actually deal with that in a pretty big way, and the same stuff happens with growth of populations. Now, you think a lot about people, but what would happen if an invasive species of like beetle got into a forest? Oh, wait, it did. A lot of people really don't realize that most of the reason why California is burning down is there was a beetle that got in there and killed a lot of the trees. If the trees are alive, they don't burn that well. But if you've got interspersed through all of the healthy trees, lots of dead trees, what do dead trees become? They become torches. And then the heat is really, really high, and it can actually light the live trees on fire. And so what happens is beetles got in, and there's just a few beetles. No big deal, right? But what does a few beetles make? More beetles, and more beetles make a lot more beetles. So if imagine you start off with 5 beetles, and every beetle made 3. 5 turned into 15. 15 turned into 45. 45 turned into 135. 135 turned into 405. 405 turns into 1,215. You with me? What do we have very rapidly? Lots of problems, don't we? Do you guys see how that works out? That's called exponential growth. Now, sometimes there will be a number sitting in front of that A. So you see that right here? So it could be like 4 times A to the X or something like that. So here are some examples. So for instance, 3 to the X or 0.5 to the X, those are known as exponentials. And what makes them exponentials, everybody, is where is the variable? Study it. Where is the variable in the story? In the exponent, and that's what makes it an exponential. So one of the things that I would like you guys to be able to do is do some evaluations. And back in the very beginning of the course, remember we had that equation inequality challenge thing, and I had you do a bunch of stuff. Do you guys remember what happened when an exponent is negative? It flips things over. Since x is a variable, is it possible that x could be negative? In fact, not only could it be, it frequently will be. So if you're going to say, hey, let's find that value, you're going to replace x with the number 2, just as we always have. That's how you do, function evaluation. So 3 to the 2 would be 9. So what would happen if instead of saying, hey, what happens if x is 2? What's going to happen, everybody, if x is negative 2? It's going to be exactly 1/9. Okay? No big deal. So keep in mind that every time you see a negative exponent, it's going to get small. But see, that's kind of strange. I want you to think about that. What happens if x was 4? I'm just going to leave this sitting right here. What would be if x was 4? 27 times 3 is 81. Okay, think about how fast that's growing. Can you picture that? It was this pedestrian little number. It was 9, no big deal. You move over 2 more units and all of a sudden it's up at 81. And if I move up 1 more, it's 243. How steep is this dumb thing? It's ridiculous. But look at the left side. If 3 to the 4th is 81, what's 3 to the minus 4th? 1 over 81. That's really small, isn't it? 3 to the 5th is 243. What's 3 to the minus 5th? That's 1 over 243. It's getting really close to 0, isn't it? There's 1 cookie and there's 243 people to share that cookie. You're going to get just this little crumb of a cookie, right? It's going to be very, very close to 0. Will it ever reach 0? As n gets bigger and bigger and bigger, but negative, it's going to be 1 over some massive number. And what is 1 over a massive number? Again, I still have 1 object, 1 cookie or something like that divide. What happens is the number of people that are going to divide that cookie goes to infinity. It's a horizontal asymptote. That's an in behavior asymptote. So they're kind of strange. They blow up on one side and go up really, really steep, but on the other side, they get really super close to 0, called a horizontal or an in behavior asymptote. So here we go. I'm going to skip over this one. I don't think it matters. Now, one of the things that you learned back in elementary school, before we kind of focus on this, is there was a time when you guys probably used beans or beads or something like that to count and kind of understand, because you were trying to come up with this constancy of math. And they would say, hey, what is 5 plus 7? And you count out the 5 and you count out the 7, and you had different techniques that you get that 12, right? And then your teacher probably at some point in time said, okay, so what is 5 plus 5 plus 5 plus 5? And then you started counting 5 and 5. And eventually you figured out there was a faster way of doing 5 plus 5 plus 5 plus 5. What was it? Wasn't multiplying a faster way of repeatedly adding things? Well, guess what an exponential is? It's a faster way of repeatedly multiplying the same thing. So in your last examination, I had a problem where we looked at a table and you looked for this repeated addition, didn't you? And you looked for the one that had that constant rate of change, correct? Well, guess what happened here? There's not a constant rate of change. There's something else. Look at it carefully. Look at G. What's happening? Every time it is constantly being multiplied by 3. Isn't it? So that means this problem is a 3 to the x power story. What's happening in H? What is constantly being multiplied? It's 1/4. So that's a 1/4 to the x story. And the same thing at mx plus b, you were looking for what was constantly being added, which turned into multiplication. Now you're saying what's constantly being multiplied to get exponential. Now here's the kind of the, I think you know this, at least I sure hope you do. Do you guys know what anything to the 0 power is? Anything to the 0 power is 1. So I'm going to kind of on purpose kind of jump over to something else. Can you write down y equals a times b to the x on your paper? You have y equals a times b to the x. And I know that I'm leaving this up here for the moment. But see, what is being constantly multiplied in function g? You tell me. What is that constant multiplier that's happening? 3. So let's change the letter b to the number 3. So let's rewrite that as y equals a times 3 to the x. Well, guys, in this exponential story, I'm almost done because the only thing I don't know is what is a. Because y is my dependent variable, x is my independent. So if I know what a is, I'm golden. Here's the point you want to find. You see right there? See 0, 4? That means if I plug in 0 for x and 4 for y, I've got what I need. So I'm going to go ahead and see if I can, let's see if I can do a quick new share to this thing right here without even killing all this thing. So if I plugged in 0 for x and 4 for y, what did I just find out, everybody? What is what is 3 to the 0 power? You said it's 1, so what does that make a? A would have to be 4. So one of the cool things about these problems, this number right there is that always what coincides with the number 0. In fact, it has to, because anything to the 0 power is always 1. Yes? See, in the story, there was a coordinate that if you plugged in 0, you got 4. So if I plugged in 0 right here, and for x, and 4 for y, a times 3 to the 0, but anything to the 0 power is 1. In other words, 4 is a times 1. I guess that means a better be 4, and it's pretty good. So let's go back to here. And so we're going to go through this idea of solving those equations. So you can see in that first one, I figured out that g was 4 times 3 to the x. Are you guys okay with that? Let's see if you can tell me what h would be. And by the way, you don't have to do a lot of work. You can literally look at it and write it down. See if you can figure out what h would have to be. Think about what your constant multiplier is. Think about what your initial condition 0 would be. So if anybody has the guts to say what they think the equation for h of x would be, Asa. Yeah.
H of x equals 8 times 1/4 the power of x.
Absolutely. H of x is 8. Where'd you get the 8 from? That was 0. That was what we would call our initial condition, where the problem started. H of x is 8 times 1/4 to the x. Did he nail it? Fantastic. Exponentials aren't that bad. You're going to have a couple of those to do in your homework. Now, when we start graphing them, this is something you need to know. In this case, I'm making a variable. You have to understand that. So I'm saying a could be literally anything, but I want you to notice what a is. It says a is above 1. So here's what's going to happen throughout today and tomorrow. Let's say a is 1.1. Can you guys do 1.1 as a percentage for me? What would a 1.1 be as a percent? 110%. Is that growing if you have 110%? Oh, you had 100%. That's your original condition, plus you gained an extra 10% on that, right? Why do they want it to be over 1? Because anything over 1, which is anything then over 100%, would grow, wouldn't it? What is 75%? That's actually you're shrinking. You're actually lost. You started at 100% and now you lost some. So anytime you have over 1, now why not 1 itself? What if you had 100% and you stayed at 100%? Are you growing? No, you're not shrinking. You're just saying stagnant. That's not growth or what we're going to call decay. So all of these graphs have this kind of feel right here. So when you graph it, every single problem is going to look like that. Does that make sense, everybody? So why on the right side is it so stinking steep? Because what happens when you start multiplying? What happens to the size of the numbers? They get big really, really fast. You follow me? They get big really, really fast. But then what's going to happen on the left? What's going to happen to all those big numbers on the left? They have negative exponents, so what's going to happen to them? They're going to flip over and they're going to become exceedingly small, very close to y equals 0. So this is what growth looks like, okay? So guess what you think, what's going to happen if it's between 0 and 1? By the way, we're never going to use negatives. We won't do it. A has to be a positive number, but not 1. Okay, so anything above 1 grows. You're going to notice the domain. This is kind of important for something that's going to come later. So the domain is every number you want. You can plug in anything you want for x, but what kind of answers can you get? Really important. You can only get positives, right? Why can't you get 0? Because if you take a number and you raise it to a power, you're never going to get 0 as an answer. It's physically impossible to do. It's going to get close, but it's not going to rate. Anybody have a guess what's going to happen if it's not above 1? What if it's like below, between 0 and 1, like 0.8 or 80%, or 0.5, 50%, or 0.01, 1%? What's going to happen? It's going to look like this. See, what happens if you take something like a fourth and you raise it to the second? It's a 16th. If you raise it to the third, it's a 64th. As x gets bigger, isn't the answer getting smaller? Oh, but what is 1/4 to the -2? That's going to bug you. 1/4 to the -2 is actually +4 to the +2. So this one, it kind of just flips the whole story out. Does it have the same domain and range, by the way? Domain is still all reals. Range is going to be positive. Does it still hit the y-axis at 0, 1? That's really important. That's my initial condition. And last but not least, does it have a horizontal asymptote? That's going to be big. So make sure you've got that one down. Those are the things that I'm going to be looking for from you. So with all that in mind, let's do our first problem. So let's go ahead and make yourself a little axis, and let's just plot a few points and see if we know what it looks like. Is 2 a constant that is above 0 but not 1? The answer is, of course, yes. Is the variable in the exponent? I believe it is. So let's see if we can come up with what this graph is going to look like. Now, I'm just going to sketch it quickly. Again, we have y equals 2 to the x. So let's make a little input-output table here. Can somebody tell me a nice number that we should definitely utilize every time? I'm going to go back. I'm going to go 0. Because what's 2 to the 0? 2 to the 0 is 1. That's right here. So I'm going to write 0, 1 right there. Some people like to use letters over here and then just put letters over here. I don't care what you do. What about, I heard somebody say 1. What's 2 to the 1? 2. What's 2 to the 2? By the way, I'm going to give up now, because what happens when I go to the 3 and the 4 and the 5 is we start getting 16, 32, 64, 128. It's going to get ridiculously large really fast. So it's going this way, isn't it? So here's A, B, and C. But what happens on the left side? What happens if someone says, let's just go back a little bit and let's try -2? What's the answer going to be for -2? If 2 to the 2 is 4, then 2 to the -2 is 1/4. No big deal. And so you come back here 2 units and you're trying to plot 1/4, and it's going to look really close to the x-axis, isn't it? Should it? But it's never going to it's never going to touch that axis. So here is what I'm calling point D. That's what an exponent, now is that growth or is that decay? As you move to the right, is that thing growing or is it shrinking? That is most definitely growth. Is it more than 100% or less than? It's definitely more. 200% is definitely more than 100%. So let's go back to this thing and carry on. So this is what this graph should look like. So notice that we just plotted a couple of points. There we go. We made this quick sketch. Life is good. So what's going to happen? So keep that same graph that you already have, and let's go ahead and bring in transformation. What the heck is going to happen? What is that -1 going to do to this story? Is it inside the parent function or is it outside? What do you think happened? It's just going to scooch all of those points down 1 unit, which means it took 0, 1 and made it 0, 0. It took 1, 2 and made it 1, 1. Ooh, what is it? What did it do to y equals 0, that horizontal asymptote? It put it at -1. So it's not that big of a deal. So what would the new domain be of this function? Wouldn't the domain of this be all reals? I mean, isn't it the blue going from negative to positive? It's good, isn't it? How about the range, though? The range used to be everything above 0. What is this one now? everything above -1. Okay, so we've got all that little information right here. So I want you guys to try to do this one yourself, please. So you got 2 to the x plus 2 plus 3. So start, if you would, please, with a couple of simple points. I think you could get away with 3, and the reason I think you can get away with 3 is, do you know what the shape of an exponential looks like every time? So I would start off with -1, 0, and 1. Find those original points on 2 to the x, and think about how it moved. We'll talk in a second. And then let's find out what those new points are going to be. Save time, I'm going to use the ones that I already have on my screen. Would these 3 points be okay? -2, 0, and 2? I think I said use 1, 0, -1, but it's the same thing. It's just 3 points, one on both sides of the axis. That plus 3, what's it going to affect? Is it going to affect the x or the y? See, what you're looking at is g of x is f of x plus 2 plus 3. That might help you, because f of x was 2 to the x, wasn't it? That was my parent function. That was the original one that we have. So what is the plus 3 going to do? It's going to move the y's up 3. So I've got 3 1/4. If I move up 3, I'm at 4. If I move up 3, I'm at 7. The original y, the horizontal asymptote was y equals 0. So if it moves up 3, I'm going to be at 3. So I've got some little asymptote kicking along here at y equals 3. What happens to all of the x's if there's a plus 2? Careful about this. What's going to happen to all those x's? What does the plus 2 do, everybody, to the x's? We've been doing for like a week now. They're going to move over which way? To the left. How far? 2 units. So -2 is going to turn into -4. -2 and 2 is going to turn into 0. And we're going to end up having a nice little graph that looks like this, that has a y-intercept up here at 7. And we have these other points down here, which are A, B, and C. And that's just kind of how those graphs are going to look. Now, is the horizontal asymptote a significant part of this graph? Draw it on there and please make sure I can see it, okay? It's a very, very important part of this graph. So I want to see that. And so they're just going to show you what I feel like might be a little bit hard to follow, is they're going to make a table out of all of those values. So I did that, but that's a little overwhelming, is it, in one big shot? But do we have those same values? See, on my original graph, I had -2 and I had 1/4. And then what did I have to do is I had to add 3 to it, didn't I? So it's all of those values. But guys, did we need 5 of them to make a decent looking graph? I think if you have 1 negative, 1 positive, and then always pick 0, because that's a very, very simple value to get, it's pretty helpful. So anyway, let's move along here a little further and I'm going to get you started. Now, before we do it, I'm not even going to do this problem. what's 3 to the x going to look like? Is it going to look like 2 to the x? I'm not sure if you guys even know. Will 2 to the x and 3 to the x look the same? Well, maybe I need to go over here and grab something that I have ready for us. So here's a little Desmos window. So guys, here's what 2 to the x looks like. It's the red graph. See it? Guess what 3 to the x looks like? It's not that big of a deal. Here's 3 to the x. It's just a little steeper, right? But that means if the numbers on the right side are bigger, what does it mean about the numbers on the left side? They're even smaller. See, as A gets bigger and bigger and bigger and bigger and bigger, it keeps getting steeper, but it forces these numbers over here to actually get smaller and smaller and smaller. See how close it is to the x-axis right here? They're phenomenally close. So I really don't want to take the time to do this because I don't think it's that valid, but like what's 3 to the 2, everybody? 3 to the 2 is 9, isn't it? What's 3 to the 0? 1. 3 to the minus 2 is 1/9. So if I took those 3 points, what is this going to do? What is that x minus 2 going to do to that 3 to the x graph? It's going to move it to the right 2 and down 1. Can you guys all move to the right 2 and down 1? So I don't think we're going to bother to go through all that, but you're going to go through this whole process. There it is. You see? Here's the point. And what did they do to this coordinate right here, negative 2 comma 1/9, is they moved it to the right 2. That's why it's 0. And what did they do to this 1/9? Did they move it down 1? The horizontal asymptote used to be at y equals 0. Where is it now going to be? That horizontal asymptote is just going to move down 1. Now, by the way, did the horizontal asymptote get moved to the right? It's infinitely long. So what happens if you take this infinitely long thing and you move it over a little bit? I'm not going to see anything. Technically, yes, it got moved over, but it's kind of dumb, right? So you're just going to see the same looking shape. And so what I'm trying to show you is what do you see if you plot point by point by point, A, B, C, D, E, all the way through that, is every single one of those should move to the right 2 and what? Down 1. And so those curves should, from geometry, be, they're congruent curves. They're literally an identical curve that somebody just moved over. So in other words, when I look at that weird graph, 3 to the x minus 2 minus 1, I don't graph it. I just graph 3 to the x, and then I scoot it over. Wasn't that easier? So we'll see very complicated curves, and we just avoid them. I just do the parent function, and then I can move it. Now, if it's 2 to the minus x, that's going to be decay. That's going to be decay, so the graph is going to end up looking like that. Now, that's weird. How does that jive with what we did in 1.6? The parent function is 2 to the x, right? What did I replace x with? And when we replace x with negative x, on that intro, I made a big deal about that. Every time you replace x with negative x, it takes that graph and it flips it across the y-axis. So instead of going this way, it comes that way, and that's called decay. So I'm going to skip over a little bit of this because I don't want to take all the time to do it, but everybody grab a calculator or grab, I don't know, I guess you could do this in Desmos, but it's a little bit weird. It's a little counterintuitive, to be honest. And this is kind of where I got to get to, and then I'm going to have you do some work. Okay. This is a super bizarre, counterintuitive little piece of mathematics that I first ran into when I was about your age too. Now, before we actually hit any buttons, I want to think about this. What happens as n gets phenomenally large? Look on the inside of this parentheses. What would happen if n got really, really big? What is 1 plus 1 over 1,000? Or 1 plus 1 over 1,000,000? What's happening to this part right here? It's getting smaller and smaller and smaller. So as n goes to infinity, what is this inside portion getting close to? No, the whole inside portion. Isn't this whole thing going to get really, really close to the number 1? This is kind of strange, so bear with me. It's going to get closer and closer and closer to the number 1, but we're going to raise it to the nth power. So let's see what kind of happens when we look at that. So here we go. Let's do 1 plus 1 over 10. I'd have too many parentheses to the 10. Now, 1 plus 1 over 10, that's not a very big number, by the way. 10 is pretty small when you're talking infinity. So, hold on, that's 1.1. So that means you have 110%, and you let it run 10 times. Is the number going to grow? Yeah. Oh, I got 2.59. You guys cool with that? No big deal. Let's hit second enter. Now, this is the fast way of doing this, and it doesn't have to be all zeros. I'm just doing it the easy way. And I'm going to come back here, and I'm going to insert a 0 here and an insert a 0 here. Now, before we hit enter, now, instead of getting 10% interest, you with me? Instead of getting 10% interest, it's not 110, 1.1. Now it's 1.01. So I'm getting 1% interest. That's terrible, isn't it? But I'm going to let it run for 100 years. Now that previous answer was 2.5937. Now it's 2.70. So I had 259. Now I have 2.704. It's getting a little bit bigger, right? What do you think is going to happen if I make it even bigger, like 1,000? Did it grow? So the fact that I am letting it go for 1,000 years, it grew, but not by that much, did it? I'm going to insert another 2 zeros because I don't want to do this for very long. By the way, when you talk about infinity, is that a good estimate of infinity, like 1 million? That's because that's not even 1 million. That's just 100,000. Is it moving much? What do you call something that as you go towards infinity, it keeps getting closer and closer and closer to some number, but it won't ever make it there? That's again, this is a crazy, weird asymptote. I'm going to go ahead and add 4 zeros. 1, 2, 3, 4. This may actually blow my calculator up. I don't know. I'm going to find out. It may give me an overflow error because I'm asking it to do probably more than it can do. Yeah, it did. But here's what happened. The further you go in that story, you get a really cool thing that is called right here. Go down, find the divided by sign on your calculator. You see it? You see in blue above that divided by sign, if you hit second and the divided by sign, it's the number E. That's the boo-boo that I made the other day when I made E of X as that last one, which is why it wouldn't graph, because E is that number. So that's kind of what just happened. In that mathematics, this is super bizarre, but as n goes to infinity, this entire thing goes to E, which is 2.718281828, and it goes on forever, and it never repeats. What does that sound like to you? Oh, it sounds like pi, doesn't it? Now here's the deal. Why does that matter? So imagine this. Let's say I took some money and I put it in the bank. And they say, I'm going to compound your interest once a year. How am I going to do for money? So they're going to give me 6% interest. They're going to give me the interest at the end of every year, and I let it sit in there for 10 years. I'll do okay. What if they say, you know what, we want to do better. We're going to go every month. By the way, I went from n equals 1 to n equals 12 in the mathematics. Am I going to have more money if at the end of every month they start giving me interest? Because that way I get interest on the interest on the interest on the interest, right? And then somebody else is like, we want your money even more. We're going to not wait for the end of the month. We're going to give you the interest every day. So now we're going to compound you 365. I gave you n equals 365. Am I getting better? You guys should understand I'm getting more money because I'm getting the interest quicker, and then I'm getting interest on that interest. It's going to help. But what you should see on that data that I showed you a minute ago, what happened when n went from 10 to 100 is it got a lot bigger. But then from 100 to 1,000, what happened? It barely moved. From 1,000 to 10,000, it barely moved. E is this crazy, crazy limit that never ever shows up, which you might go like, what stupid bank would do that? It's called nature. Nature doesn't wait. When the wood is out in the forest and it's rotting, does it rot and wait like exactly 2 weeks and all of a sudden it just degrades a little bit, like a big, you ever see that happen? Like all of a sudden it goes, poof. Or does it just gradually happen? That's called continuous. Continuous growth and decay. Here's another one. Imagine, if you will, that I took out a piece of really, really, really hard, hot steel and I put it in the room. Would it change the temperature of the room? Should. That's also an exponential, and it's also going to involve E. In fact, anything that happens in the real world, if you're going to have growth or decay, that's like radioactive plutonium, all of that kind of stuff. Real life story, it's always E, everybody. That's just what it is because it doesn't wait for a certain time for it to happen. It's always happening. So the increment of time is basically zero. In other words, we're doing an infinite number of those things. And so where is this 2.72 coming from? That's that crazy number E to the first power. Cool? What do you think this one is? It's that crazy number E to the second power. See? E to the second power. E to the, what is this one right here? That's E to the -1 power. So that's the graph of E to the X, which is actually you saw for the first time in section 1.3. That's the exponential function that I want you guys to be able to do. So this is, they will call this one a transcendental number. You guys ever heard of the word transcendental? You'll hear of transcendental meditation, but that's kind of dumb. But that's a different issue. But it's a transcendental because, is it an important number? Was pi important? Does it show up in nature? Yeah. It's one of those things, but it's so crazy. We kind of understand it, but we kind of don't totally understand it. There's another one that's really cool. Have you ever heard of the golden proportion? I saw one shake of a head. You heard of the golden proportion? It's really strange. You would not even believe this. I'll actually show you what it is. There's actually two of them. This is so bizarre. Oh, you can't see that. I need to go back to here. Let's go to here. And by the way, it has a little bit of a feel that looks like that other one, but it's 1 + √5/2. That's another weird number that never repeats and it shows up in nature. Do you know that if you actually look at a really healthy plant and you actually measure the gap between things and you find the ratio of like how far the limbs are, that's what shows up? If you show a list of faces and find out what is the one that looks the best to your eyes, the ratio of this to this on their face will be that one. In fact, it's all over the place in nature. Again, we don't totally understand why that happens, but it seems to be the thing that maximizes. In fact, that when you look at, like, I think it's the ratio as you go through in a sunflower seed. Sunflower, have you ever seen a sunflower, like with all the things? There's a spiral that actually happens, and this number shows up in the spiral in that sunflower seed. It actually also shows up, do you guys know like white four-leaf clovers are such a weird thing? I'm getting a little off task, but here's what happens. This is nature. This is called the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13. These are what show up in nature. Did you guys know that? I don't know if you've ever seen that. It's called the Fibonacci sequence. See how 1 + 1 is 2, 1 + 2 is 3, 2 + 3 is 5? So these are the things that show up in nature. Yeah, the number 4. It's not there, is it? It's not supposed to be there. So if you find a four-leaf clover, you found a mutation. And what happens as you go towards infinity and you start dividing these numbers up, the further you go towards infinity, the more it becomes that number. And so as plants effectively evolve or whatever to like maximize sunlight exposure, blah, 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 boom, that number, the ratio as you go out shows up, and it's like everywhere. They call that a transcendental number. It's like a number that's so dang important that we need to study it, but it's kind of blows our mind away because we can't really truly fully get it. So that's kind of a cool thing, and E is one of those numbers. So you do need to be aware of that E is a very important little sucker. It's that thing. So we do it all over the place. And so that's kind of where we're going to kind of kill today's lesson. So on your packet that I gave you, and that packet looks like it's big because it is. It took me a long time to make. That's actually going to take us through today and tomorrow. I'm trying to slow things down. It was going to be just today, but I held off. So on that packet, I want you to get going on it, but we're not going to get through the whole thing today. We're going to not get to the application piece. So I would like you guys to look at this thing and just go through the following stuff. Figure out which ones are exponentials. I think that should be fairly simple. Learn how to evaluate. Learn how to come up with the equation that works. Now, occasionally, if you guys get stuck, I'll stop you and we'll go over some things. But I would like you to try, if you can, to make it through the first 3 pages. Okay? And that's going to kind of end the day today. So you guys have about a half an hour. And I'm going to go ahead and stop.